In this video, I would like to analyze some properties of optimization problems. Actually, from now on, I will only consider minimization problems because we have seen that you can always transform a maximization problem into a minimization problem. The idea of the video is to provide some intuitions about these properties. If you want a more rigorous development, I refer you to the book, to section 1.4, where all the equations will be actually derived. So let's look at this function, f of x equals minus x, and let's try to solve the optimization problem, minimum of f of x equals minus x. So we would like to find the value of x, which makes the value of minus x as small as possible. Well, the problem is that this does not exist because the function is not bounded from below. We can always go further away to the right to positive values of x, and it will always decrease the value of the objective function. So there is no way to find a minimum of this function. It is not well defined. For an optimization problem to be well defined, we need the objective function to be bounded from below inside the feasible set. The fact that the objective function is bounded from below is not sufficient to make sure that the problem is well defined. And in order to illustrate that, let's take this example where f of x is equal to e to the minus x. In this case, f of x is bounded from below because f of x is always non-negative. Actually, in this case, f of x is strictly greater than 0. But the problem is that we cannot find an optimal solution, so we cannot find a point x such that x has the smallest value of the objective function in the real set. Indeed, if you give me any x, I can always find a x which is better, typically x plus 1. We have e to the minus x minus 1, which is strictly less than e to the minus x. So there is no way to find the lowest point because whenever you give me a point, I can always find a better one, whatever it is. Here we will have to distinguish between two different concepts. The concepts of infimum, and I will call it the infimum of f of x. This is defined as the largest lower bound. In the case of this example, the largest lower bound is actually 0. And we'll define the optimum, which is the second concept, which will be x star, as we defined in a previous video, such that the value of f at x star is equal to the infimum. And in this example, there is no such x star. So the infimum is equal to 0, but the value of the objective function is never 0. There is no x such that f of x is equal to 0. So there is no optimum. So it's important for practical reason to understand the difference between these two concepts. It's not because a function is bounded from below that there will be an optimum. There are some theoretical results that identify when an optimum exists. For example, there is a theorem attributed to Weierstrass that states that if you minimize a function over a non-empty compact set, you have the guarantee that an optimum exists. So let's provide the formal definition of the infimum and the optimum. So as we say, the infimum is the largest lower bound of the function. So the infimum of f of y for y belonging to the feasible set is a lower bound, so it's less or equal to f of x for any x. And it's also the best one. So if you take any value which is larger than the infimum, strictly larger, it cannot be a lower bound. It means that there is at least one x such that the value of big M is bigger than the value of f of x. So this is the definition of the largest lower bound. This is what we call the infimum. And the optimum is a vector x star of decision variables such that the value of the objective function at x star is equal to the infimum. A concept which is interesting in terms of defining the constraints is an interior point. Intuitively, an interior point is a point which is at the interior of the constraint, so which is somehow away from the boundaries of the constraints. So let's consider this simple example where we want to minimize this quadratic function under the constraints that x must be between 0 and 2. And you can verify that the optimal solution is at x equals 1. Now let's consider the other problem without constraint that consists in minimizing the quadratic function. Well, as you can see, you will achieve the exact same solution. So somehow here the constraints do not play any role. The reason is that the point x star, the solution, is an interior point. So what is an interior point? An interior point is a point such that whenever you take an interval around x star, all the points within the intervals are feasible. So somehow it means that x star is away from the boundaries of the constraints. We will also say that the constraints are not active. And in this case, somehow, they don't play any role at the solution. So we don't have an equivalent problem, so to speak, because there are some feasible solutions of the second problem which are not feasible for the first one, like x equals 3, for example. But both problems have the same optimal solution. And so sometimes it will be convenient to ignore constraints that are not active in order to simplify the model formulation. So in this video, we have seen that an optimization problem is not always well defined. A necessary condition is that the function must be bounded from below on the feasible set. We have seen that it is not sufficient. Sometimes we can have functions that are bounded from below, but that are not achieving any optimum. We have also seen that some optimization problem can be simplified by removing constraints that do not play any role at the solution. And this will be exploited in the future.